Hi everyone, my name is Sepide. I'm Technical Solution Specialist from Israel, Canada. In this video, I'm going to talk about the best practices for working with airborne LiDAR data in ArcGIS Pro to efficiently extract information from it. I will show you how you can create 3D buildings with an accurate roof form as well as trees with an accurate height. ArcGIS supports LiDAR data provided as LAS or ASCII files. LAS files are an industry binary format for sharing airborne data. This LiDAR data covers the city of Fredericton in downtown neighborhood. Working with LiDAR data requires ArcGIS Pro Advanced license with Special Analyst and 3D Analyst extensions. Before starting to work with LAS files, always make sure that they are projected. Also make sure that the large LiDAR data are clipped and they are filtered. ArcGIS Pro offers ExtractLAS tool to clip and project LAS files. When LiDAR data is added to the map display for the first time, it will be drawn in a way that you cannot differentiate between buildings and vegetation in it. ArcGIS Pro 2.3 has a set of tools for visualizing LAS files. You can symbolize LAS files using slope, contour, or class code method. We can differentiate building rooftops from high vegetation. As you see, red points represent building rooftops and green represent high vegetation. Airborne LiDAR should be classified into ground, vegetations, and buildings. However, it's not uncommon to receive LAS file format that doesn't have the building classification code. Set LAS class code using features is a geoprocessing tool that helps us to assign building class code to a LAS file. This tool uses the building footprint to identify building class code. LAS points sometimes are classified incorrectly. For example, in this area we have building class code instead of high vegetation code. Manually editing LAS points are the best way for correcting the classification code. Pro allows us to select points that have incorrect class code and change their class codes. All changes in this way are permanent. If you are conducting any what-if scenarios or you don't want your changes to be permanent, make sure to work on a copy of LAS files and not the originals. Let's talk about another consideration. Always access your LAS files through LAS dataset. LAS dataset provides fast access to large volumes of LiDAR without the need for the data conversion or importing. LAS dataset tool helps you to combine all your LAS file into one file. LAS dataset can be used as an input into other geoprocessing tools. Also, we can symbolize LAS dataset with the classification method. Let's move on to the second part of our video, which is creating 3D buildings from last dataset. All the workflow that I'm going to show you now, you can find it in the local government 3D base map. There is a hands-on lesson that takes you through steps that I'm going to show you. You can download the local government 3D base map package from ArcGIS Online, but you can deploy this solution using ArcGIS Pro. This map package contains tasks that take you through pre-configured steps for creating 3D buildings with an accurate roof form. First thing we need to do is calculating the height of these buildings by subtracting digital terrain model from the digital surface model. Let's start with creating a digital terrain model. We need to filter last dataset to select only the ground points. Now we can use this last dataset as an input into last dataset to raster geoprocessing tool. Sampling value plays a very important role. It defines the resolution of our output. So make sure to put a valid number in this parameter. Check the point spacing value in the property of your last file. In this scenario, our point spacing is 0.27 meter. Now I'm changing the sampling value to the number close to my point spacing. The darker area showcases the lower elevation, and the lighter area represents higher elevation. After our DTM is generated, you can use raster function tools to extract more information about your ground elevation. Let's create hillshade. Hillshade is a good example for extracting more information from your DTM. It helps you to provide different interpretation about your ground raster. Let me zoom to some part of this hillshade. Now it's time to create DSM, Digital Surface Model. This DSM is a raster that each cell captures the elevation of features elevated above the ground, such as buildings and tree canopies. This time, we need to filter last dataset to select building and vegetation. And now we can use this last dataset as an input into last dataset to raster geoprocessing tool. Use the same value that you used for DTM for the sampling value. As you see, dark cells represent lower elevation and light cells represent higher elevation. The final raster we need is normalized raster. We can subtract DEM from DSM using minus tool to calculate the surface differences. Let's zoom closer to this raster. This is the raster that captures the roof height information. Now it's time to use ExtractReform, which is a Python code created by Esri. This tool creates a new building footprint. Also, it creates and adds building height, eave height, roof form, and roof direction in the attribute table of new polygon. It requests for your building footprint, your DSM, your normalized raster, and your digital terrain model. You can download this tool from the local government 3D basemap project package. I've already run this tool and let me show you the output of this tool. It's recommended using this tool when your point density is less than 1 meter. I open the attribute table of this tool and you see that building height and roof form get extracted from digital elevation models and is added to the new polygon. Now it's time to extrude the polygon. Apply symbology from layer tool can help to create 3D buildings polygon with an accurate roof form. It uses LOD to building layer. You can download LOD2 building layer from local government 3D basemap project package. Now let's look at the result of our 3D polygon. What we have right now, it's only polygon that has 3D symbology. I will show you later how you can convert this polygon to multipatch. At this step, you can edit the roof forms and change building height. Let's zoom to the one of the building to edit the roof form and building height. As you see, this building has gable roof form. Let's change this roof form to flat. So attribute has different type of roof form. Let's select the flat roof form. And don't forget to save your edit. This 3D layer cannot preserve 3D symbology in its property, and it cannot be shared as a 3D object. That's why we should convert this 3D polygon to multipatch feature. Layer 3D to feature geoprocessing tool help us to convert a 3D polygon to a multipatch feature class. Multipatch feature class is a geometry type that represents the boundary of 3D objects. It's a collection of patches that stores textures, colors, and transparency and geometry information of a feature. Let me zoom to the multipatch feature. Now this layer can be edited using edit tools. Let's edit one of these buildings and change the roof form from flat to gable using vertices tool. Also, I can load the textures and images to this multipatch building. Let's add a facade to this building. Also, we can pan, rotate, and zoom our picture to adjust the picture to our multipatch feature. After you load your picture, you can apply texture to the multipatch, and you can save your edit. Let's move on and talk about importing 3D models into Multipatch Feature class. One of the enhancements in Pro 2.3 is supporting 3D model formats. We can import 3D Studio Max, Collada, Wavefront Object Model, and OpenFlow to Multipatch Feature. Let's import a few high-rise buildings into this multipatch. Let's add another one. And save our edit. Let's talk about procedural symbology. Procedural symbology can be used to render multipatch features with rule-based painted textures. Sometimes it's very time-consuming to add a texture to each building. In this case, you may want to use City Engine rule packages to add a texture to your building. You can find and download rule packages in ArcGIS Online and export them in ArcGIS Pro. Let's add City Engine rule to the symbology pane. I'm going to modify the parameters and apply them to the buildings. Let's look at the result. Now it's time to create realistic looking trees. Vegetation extraction tool can extract and calculate vegetation height from last dataset. You can find this tool in the Local Government 3D Basemap project package. This tool is using DTM, building footprint, and selected vegetation class code to create the point feature class to represent trees. Let's start with filtering our last dataset. Then I use this last dataset as an input into vegetation extraction tool. We can use the same point spacing that we used for our DEM. The class code vegetation will be number 3, 4, and 5. Add your building footprint and provide a digital terrain model. I already ran this tool, so the result of this tool is point feature class. Now I can take this point feature class and create realistic trees from it. Let's select the tree type from the pane. Let's look at the result as well. Let's move on to the final step, which is sharing our work with others. Let's take a trees and building footprint and publish it into new local scene. Under Share tab, you can select the web scene and provide the name, summary, and tags. Let's analyze to make sure that there is no problem for publishing our work to ArcGIS Online, and let's share it. Let's check the job. The job status helps you monitor progress of caching your layer into ArcGIS Online. And if the process fails, attach log file helps troubleshooting the problem. Now it's time to look at the published web scene in ArcGIS Online. These are published web scene and associated scene layers in ArcGIS Online. Let's look at our web scene in Scene Viewer. Thank you for watching this video.